Hi, welcome to the 12th week tutorial session of NPTEL course, Principles of Hydraulic Machines and System Design. This is a problem solving session regarding the last week lectures of this course. Before the final exam, we will be conducting another session to revise all the previous lectures questions, some numerical questions and multiple choice questions. But in this week, we will basically deal about the last week lectures that comes from Kaplan turbine, the draft tube, net positive suction head and cavitation, and the unit speeds and specific speed, unit quantities and specific speeds. My name is Ananthakrishnan. I am a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. Before wasting much time, we can move to the questions. We will discuss a few numerical based questions and multiple choice questions in this week. And first of all, we'll go to the numerical answer type questions. Yes. This is a numerical answer with multiple choices in it. This is a problem regarding Francis turbine. In a proposed hydroelectric power plant, 282 cubic meter per second of water is available under a head of 3.7 meters. Francis turbine with specific speed 2.42 is intended to be used for this plant, for which the rotational speed is 50 rpm. If the turbine efficiency is 90%, the number of turbines required will be 1, 3, 6, or 10. A question which is based on the Francis turbine specific speed, and we need to get the number of turbines which is required. In this particular problem, we need to determine the power produced by a single turbine. The power produced by all the number of turbines can also be calculated. From that, from these two quantities, we can calculate the number of turbines which is required. So in this particular problem, the specific speed is given as the formula is n root p divided by rho raised to 1/2 into gh raised to 5/4. This is the dimensionless form of the specific speed. If it is a dimensional form, that will be in the terms of n root p divided by h raised to 5/4 when it comes to the turbines. From this, we can calculate the power P, power produced by a turbine is denoted by P. So P is equal to NS rho raised to 1/2 GH raised to 5/4 divided by speed, the whole power, the whole raised to 2. So the NS value, the quantity of NS is 2.42, the specific speed. Rho is water. So that will be 1000 into G is 9.81 head is given as 3.7. And the speed is given as 50 RPM. So in terms of so in this particular dimensionless form, the specific speed should be in terms of radian per second term. So this n should actually be corresponding to radian per second or omega term. So the omega can be represented as 2 pi n by 60. So we will represent omega in terms of 2 pi n by 60. So instead of writing this, we can write this in terms of omega s and in terms of omega. We substitute these values and we'll get this value. So in this particular space, this omega non-dimensional form, this is specific speed in the non-dimensional form. So that's why we have to write it specifically. And this should be in terms of radian per second. So based on that, we'll be getting this value. So this whole term power 2. So that will be the power for a single turbine. So the power P is equal to 1.697 into 10 power 6 Newton. So this is the power produced by a single turbine. Next, we need to calculate the power produced by all the turbines combined together. The head remains the same in this case. So we can calculate this to be equal to efficiency multiplied by the actual power produced by all the turbines together. The actual power which is available at the inlet to the turbines. So efficiency is given as in this particular problem 90%. The turbine efficiency is given as 90%. So we can use 0.9 rho 10 cube G 6.81 and the in this particular problem the total flow rate for all the turbines combined together is 282 meter cube per second. So we can use 282 multiplied by the H remains the same for all the turbines. That is 3.7. So the power produced by all the turbines is equal to 9.21 into 10 power 6 watt. Therefore, the number of turbines required to produce this much power is equal to power total divided by power individual. So that is 9.21 divided by 1.697. So that will come to be around 5.42. If you round it out, that will come now to be 6. So the number of turbines required is 6. This question was to determine the number of turbines based on the total power produced by all the turbines together and the power produced by individual turbine. So you can determine the actual power produced by a single turbine from the specific speed analysis. Dimensional specific, note that it is dimensional specific speed. So we have to include the RPM, the speed value in terms of radian per second. And from that we'll get the power which is produced by individual turbine. Based on the efficiency, we can calculate the power which is produced by all the turbines combined together. And using these two parameters, we can determine the number of turbines required to achieve the overall power. Look into the second problem. This is quite similar to that of the first problem, but here the dimensionless parameters are jet ratio, speed ratio, and overall efficiency and coefficient of velocity. And this is regarding a Pelton turbine. In a projected hydroelectric power plant, a Pelton turbine needs to produce 15 megawatt power by working under a head of 480 meter and running at 500 RPM. The jet ratio is 10, speed ratio is 0.46. Overall efficiency is 85%, and the coefficient of velocity is 0.97. Determine the minimum number of jets required to drive the turbine. The options are 1, 2, 3, and 4. So in this particular problem, we can denote the parameters which are given in this problem. First of all, this is a Pelton turbine that needs to produce 15 megawatt power. The operating head is 480, which remains the same, and it runs at 500 RPM. The jet ratio is given as 10. Speed ratio is 0.46. Efficiency is 85%, and the coefficient of viscosity is 0.97. So this jet ratio actually corresponds to the diameter of the wheel to the diameter of the jet, that is 10. Then corresponding speed ratio is 0.46. So the speed ratio is the ratio between the blade velocity to the actual velocity at the inlet. And the overall efficiency, eta overall, is equal to 0.85. and also the coefficient of velocity in the nozzle is given as 0.97. We need to calculate the number of jets that is required to drive the turbine to produce the total power of 15 megawatt. So in this particular problem, we should calculate the number of jet. For that, we require the actual velocity, the actual volume flow rate that is required to produce in the case of Pelton turbine. In order to produce the overall power, we need to calculate the actual, the total actual volume flow rate that is required to produce this power, and the volume flow rate that is associated with the jet. Dividing the total volume flow rate to the volume flow rate of each individual jet, we can determine the number of jets, minimum number of jets that is required to drive the turbine. So first of all, we need to calculate the actual volume flow rate. For that, we determine the actual volume flow rate from the overall efficiency, eta overall. The formula for the overall efficiency is given as the power produced, the actual power produced divided by power which is available uh, corresponding to the fluid kinetic energy at the input. And overall efficiency will take into account the head which is available at the inlet of the Pelton turbine and the outlet power. So the fluid energy can be represented in terms of uh, the volume flow rate and the height or the head from which the fluid is coming from. Correspondingly, we can determine the total volume flow rate. Q is equal to P divided by eta overall into rho G into H. The power P is equal to 15 megawatt, 15 into 10 power 6. Efficiency, overall efficiency is 0.85 multiplied by rho is 10Q, G is 9.81, and head is 480 meters. And correspondingly, we'll get the total volume flow rate. Q is equal to 3.75 meter cube per second. And then we should determine the volume flow rate that is associated with a single jet. For that, we need to find out the diameter of the jet and as well as the velocity of this jet. Velocity of the jet is actually the actual volume, actual velocity, and we can determine there is a coefficient which is given in this problem, that is a speed ratio. If you know the blade velocity, we can determine the actual velocity at the inlet, and also the jet ratio is also given. That is the ratio between the diameter of the wheel, diameter of the Pelton turbine wheel to the diameter of the jet. We can determine the diameter of the jet from these coefficient. Using these two, we can determine the volume flow rate of each individual jet and the corresponding total number of jets. So in this particular problem, velocity actual velocity of the jet or the velocity inlet to the turbine wheel C1. We can calculate this value C1 using the coefficient of discharge and the coefficient of velocity in the nozzle multiplied by root of 2gh. So this takes into account the losses which happens within the nozzle. So coefficient of velocity CV is 0.97 and the corresponding velocity before the nozzle is represented in terms of root of 2gh. H is 480 meters. So using this, we'll get C1, the actual velocity C1 as 94.13 meter per second. And we can calculate the blade velocity or the peripheral velocity U from the speed ratio. So speed ratio is given as U divided by C1. Therefore, U is equal to speed ratio into C1. So this quantity corresponds to speed ratio into C1. So speed ratio will correspond to 0.46 multiplied by 94.13. That is coming to be around 43.3 meter per second. And we can determine the diameter of the wheel from the value of U. U is equal to pi d n by 60. D is equal to 60 U divided by pi n. So 60 into 43.3 divided by pi into n is the RPM which is associated with the wheel. So in this particular problem, it's known as 500. And we get the value of 1.65 meters. And in this particular problem, the jet ratio is given as 10. So that is a ratio between diameter of the wheel to the diameter of the jet. So the diameter of jet will be equal to d by 10, that is 0.165 meters. Therefore, the volume flow rate of water in a single jet is given by pi by 4 into d squared into the velocity. So that is becoming around 2.02 meter cube per second. So that number of jets required is equal to the actual volume flow rate divided by the volume flow rate in the individual jet. So that is equal to 3.75 divided by 2.02. That is equal to 1.85, and we can approximate it to be 2. So in order to achieve the volume flow rate, total volume flow rate, number of jets required is equal to 2. We determine the actual volume flow rate from the overall efficiency and the power which is given, and the head value also. And for each individual jet, we need to calculate the volume flow rate. We need to, for that, we need the diameter. We can get the diameter from the jet ratio, and also we need to calculate the velocity of the jet. Velocity of the jet we can calculate from the uh, free flowing velocity term and multiplied by the coefficient of viscosity, coefficient of velocity. So, and we need to determine the diameter. We need to determine the peripheral blade velocity from this actual velocity term. And using the peripheral velocity and the RPM, we can determine the diameter of the blade or the diameter of the wheel. And using the diameter of the wheel, we can calculate the jet diameter. And using this jet diameter and the jet velocity, we can calculate the coefficient of, we can calculate the discharge which is associated or the flow rate which is associated with the jet. And using these two flow rates, the actual flow rate and the jet flow rate, we can calculate the number of jets required to produce the power. Now we can move to the next problem. In this problem, we need to calculate the head, the flow velocity and peripheral velocity of an inward flow reaction turbine are 4 meter per second and 35 meter per second respectively. The wall velocity at the inlet is 6 meter per second, while there is no wall at the exit. Hydraulic efficiency is given as 91%. The available head would be 11 meters, 102 meters, 324 meters, and 638 meters. This is a straightforward problem. We need to calculate the head which is available at the inlet. For that, we know the efficiency, hydraulic efficiency. Using this hydraulic efficiency, we can calculate the hydraulic efficiency is actually the ratio between the actual head produced and the head which is available at the head which is available at the inlet. The head in terms of the power. So if we know the wall velocity component as well as the blade velocity component at the inlet to the turbine, reaction turbine, we can calculate the head which is required at the inlet to determine to produce the same power based on the hydraulic efficiency. First of all, we need to draw the inlet velocity triangle. Since the wall at the outlet is 0, we need not worry about the wall component at the outlet. And we need not draw the velocity triangle at the outlet. But what we require is a velocity triangle at the inlet to determine the so in this particular problem, all the parameters are not given. The flow velocity component and the peripheral velocity component are given, and the corresponding wall velocity at the inlet is also given. Since the peripheral velocity is given and the wall velocity is given, we need not worry about the inlet velocity triangles. Every value is given, and we only need to calculate the head from the efficiency term. So the hydraulic efficiency is given as W1 U1 divided by GH. From here, the head H is given as VW1 U1 divided by G into hydraulic term. So in this particular problem, the wall velocity at the inlet is given as 6, and peripheral velocity is given as 35 meter per second. G is 9.81 into 0.91. check how much is coming. I beg your pardon, there is a small correction in the value. The world velocity at the inlet is given as 26 meter per second. So we have to correct this to 26. So the value will be coming around 102 meters. The answer is B. So in this particular problem, almost all the values are known. We know the value of the blade velocity. We know the value of the whirl compound at the inlet, the peripheral velocity, and the hydraulic efficiency. We can calculate the head from this formula direct, straightforward. But if one of these parameters was unknown, we could have calculated that from the velocity triangle. If some other parameters of blade angle was given. In this particular problem, for instance, if the peripheral velocity was an unknown, we could have calculated that from the flow velocity term and the whirl velocity term at the inlet. Uh, and one particular value of the blade angle should also be present. Look into the fourth problem. So in this particular problem, the question is regarding a Francis turbine working under a head of 25 meters. It develops this much power, and all the three efficiencies are given. Diameter and the blade width values at the inlet and the exit at the outlet are given. The runner blade angle θ1 at the inlet is also given. We could assume zero whirl at the exit. Tangential component we can ignore so that it will become easy to calculate the power. Determine the blade velocity, that is the relative velocity at the inlet. That is the problem. So we need to draw the velocity triangle to determine the blade velocity at the inlet. So you draw the velocity triangle. This is the actual velocity at the inlet. The blade angle between blade, the blade angle between the relative velocity term and the peripheral velocity term is given as 135. So this obtuse angle will be equal to 135 degree. So θ1 corresponding, this will be the relative velocity term for the blade velocity term. So we need to calculate this particular value. So we can denote it by W1. That will be a bit more easy to understand coherently. So this one will be the peripheral, the blade velocity. In this particular problem, there was a small correction. We need to determine the blade velocity. The blade velocity term is U1 term. This W1 term is the relative velocity. This is the actual velocity. We need to calculate the U1 term from this velocity triangle. This is θ1, and corresponding this one will be the alpha1, and this one will be the flow component of the actual velocity, and this term will be the whirl component of the actual velocity term. So we need to calculate the blade velocity. So the blade velocity we can calculate from the in the velocity triangle. From the velocity triangle, taking the taking this particular triangle, after knowing the flow velocity term and this particular value, based on uh, this angle, we can determine the rest of we can determine the value of the blade velocity u. But for that, we need to determine the flow velocity term and the whirl velocity term of the actual velocity. And using this angle of 45 degree and the tan of these two, we can determine the blade velocity. So first of all, we have to from this particular problem, we need to determine the flow velocity component of the actual velocity and the peripheral and the whirl component or the tangential component of the actual velocity at the inlet. So we can note down the important parameters that are given in this problem. It is given as 25 meters. The power produced is given as 2555 kilowatt. Volumetric efficiency is given as 0.98. Actual the mechanical efficiency is given as 0.97. Overall efficiency is given as 0.9. So the important parameters that connects the power produced by the blade to the power which is available at the inlet to the blade or the runner blades, or runner in inlet to the runner power which is available, that important parameter that connects is the hydraulic efficiency. From the volumetric efficiency, mechanical efficiency, and overall efficiency, we can determine the hydraulic efficiency. So the hydraulic efficiency theta hydraulic is equal to overall efficiency divided by the volumetric efficiency and multiplied by the mechanical efficiency. So that will be 0.9 divided by 0.97 into 0.98. That will be coming around that is coming around 0.946. And using this hydraulic efficiency and the power produced and the power which is available at the inlet, we can determine the actual flow rate. So the flow rate or the discharge Q is given as the power produced divided by the overall efficiency multiplied by rho into G into H. So from this we can determine the flow rate. The power which is produced at the end is given as 2255 kilowatt. To 10 cube. Overall efficiency is 0.9 10 cube divided by, and the height is given as 25 meters. So the flow rate or discharge is equal to 11.57 meter cube per second. And this flow rate, from this flow rate, we can calculate the flow velocity term. The another formula for flow rate Q is equal to 5 T1 P1 into Vf. So we can calculate the flow component, flow velocity component from this particular formula. Flow velocity component is Q divided by pi T1 into P1. So it comes around 11.57 divided by pi into diameter at the inlet in this particular problem is given as 1.31 meters, and the width at the inlet is given as 0.38. So the answer is 7.4 meter per second. So we have calculated one important parameter, the flow velocity component. Now we need to calculate the mole component of the velocity, and using both these parameters, we can determine the blade velocity parameter component. And we have calculated the hydraulic efficiency from the previous analysis. Hydraulic efficiency, we determined it to be 0.9467. So that is equal to the power produced by the turbine divided by G into H. From this one, we can have a relationship between VW1 and U1 Pw1 U1 is equal to 0.9467 into G into H. That gives Vw1 U1 is equal to 232.195. Mark it by 2. Equation 2. From the velocity triangle which we have discussed, this triangle, this section, right hand side, right angle triangle. From that, the supplementary angle to the blade angle, that is 45 degree, and taking a tan of that, we can have a relationship between the flow velocity component, whirl component of the actual velocity, and the blade velocity component. So from the velocity triangle, tan of 180 minus 135 is equal to CF1 divided by U1 minus CW1. So tan 45 is equal to CF1 divided by U1 minus CW1. So we will get another equation that connects the blade velocity component and the whole component of the velocity. So I beg your pardon, there was a small correction. This is CW1, not VW. So CW1 term. This is the we'll get U1 minus CW1 is equal to 7.4. Denote it by 3. Now we have two equations between that connects U1 and CW1. Solving them simultaneously, we will get U1 is equal to, you will get a quadratic equation. So it will come to be, so when we substitute the value of VW1 from the previous, in the equation 2, VW1 U1 is equal to 232. So substituting VW1 is equal to U1 minus 7.4. We get U1 into U1 minus 7.4 is equal to 232.195. So that will be equal to U1 squared minus 7.4 U1 minus 232.195 equal to 0. That will give the U1 value is equal to 19.38 meter per second. So that solves this problem. The question was to determine the blade velocity. So the answer is option 1. In this particular problem, from the velocity triangle, we can form a relationship between the flow component, the whirl component, and the blade velocity. Then in order to determine the blade velocity term, we need to know the flow component and the whirl component of the actual velocity. Flow component of the actual velocity can be determined from discharge and the area of cross section that involves the diameter as well as the blade width. So the discharge we can calculate from the overall efficiency term and the power and the head which is given, and using that we can determine the flow velocity component. And the whirl velocity component, in order to determine that, we need the hydraulic efficiency term. The hydraulic efficiency term, we can formulate a relationship between the blade velocity term and the flow velocity component and the whirl velocity component. So we have two equations that interconnects the blade velocity as well as the whirl velocity component, and then we solve set of simultaneous equation and it will form a quadratic equation. By solving the quadratic equation, we can get the value of the blade velocity. We got it to be 19.3. Look into the fifth problem. So this question is regarding the peripheral velocity of a Pelton wheel. It is given to be 25 meter per second. The incoming jet, which has a velocity of 65 meter per second, is deflected by the bucket at 160 degree. The flow rate is given as 0.9 cubic meter per second, and the blade friction coefficient is 0.9. We need to determine the hydraulic efficiency of the turbine. To determine this, we require the velocity triangles. At the inlet, there is no triangle. Since it's a Pelton wheel, it will be a straight line where this is the actual velocity C1, and if this is the blade velocity at the inlet, this one will be the relative velocity V on W1, and the whole term is the wall velocity at the inlet. And it's meant that the Pelton turbine deflects the uh, jet by 160 degrees. So the inlet velocity triangle will be this one. Outlet will be deflected by 60 degrees. So the relative velocity will make an angle 160 in this direction. Correspondingly, in this direction, it will be 20 with respect to uh, the initial flow, initial velocity direction. Correspondingly, this is U2. In this case of Pelton wheel, U1 is equal to U2. This is the actual velocity C2. We need to make it a bit more coherent compared to previous weeks. I can make it slightly smaller, the value. The actual velocity at the inlet. Just C2 is U2, and this component of C2, that is the flow component at the exit or the outlet, and this is the wall component at the uh, outlet. Here, C corresponds to actual velocity, W corresponds to relative velocity, and U corresponds to blade velocity or the peripheral velocity. So in this particular problem, the jet velocity at the inlet is given as 65. So C1 is equal to CW1, which is C omega 1 or C theta 1. Theta 1. C theta 1 is equal to tangential component is equal to 65 meter per second. The blade velocity at the is given as 25 meter per second. We can determine the relative velocity W1 is equal to C1 minus U at the inlet, that is equal to 40 meter per second. In this particular problem, the friction coefficient is given as 0.9. That blade friction coefficient V is a ratio between the relative velocity at the inlet W2 minus W1 is equal to 0.9. So we can determine the relative velocity at the outlet W2 is equal to 0.9 into 40 equal to 36 meter per second. Correspondingly, from the velocity triangle, we can determine the tangential component C theta 2. C theta 2, we can determine from the value of blade velocity as well as the horizontal component of the in this triangle, right angular triangle. We can determine the value of the c theta 2 or the tangential component of the actual velocity at the exit is equal to the tangential component of the relative velocity of the exit minus the blade velocity. That is equal to c theta 2 is equal to W2 cos 20 minus 25. This is the U component. U2. So W2 is 36. 36 into cos 20 minus 25. So that is equal to 8.828 meter per second. So we determine the blade the tangential component of the axial velocity at exit. We know the tangential velocity of the tangential component of the axial velocity at the out inlet. We also know the peripheral velocity. So we can determine the hydraulic efficiency in the case of Pelton turbine. Equal to V Dept is C theta 1 plus C theta 2 into U divided by C1 squared divided by 2. That is the inlet kinetic energy of the fluid. So the hydraulic efficiency in the case of Pelton turbine will be expressed in this formula. Since the fluid takes a 180-degree turn, the outlet velocity will be in a negative directional set of the inlet velocity, and because of that, the whole terms gets added up. The magnitudes gets added up. So C theta 1, we know 65, and C theta 2, 8.828 multiplied by 8.828 multiplied by the U value, that is 25, divided by 65 squared divided by 2. So we'll get it around 0.8737. So the hydraulic efficiency equal to 87.37%. So that is the answer. So the answer is option 4. So very straightforward. We have to determine the tangential component of the velocity at the inlet and exit, and using this and using the formula, standard formula of hydraulic efficiency, we can determine it. So this is a multiple choice question. Which of the following turbines does not require a draft tube? Francis turbine, Kaplan turbine, Pelton wheel, none of them. So the answer to this question is Pelton wheel. Draft tube is used in certain cases where the actual available head is very less for the turbine to operate without to produce the same power. So if there is an issue with the head which is available, we need to maximize the head which we can generate from the turbine, and that uh, maximization of the head resulted in the innovation of draft tube, which makes sure that the available kinetic energy at the exit of the turbine will be converted to the head by fitting a by fitting a conical tube at the end. So in the case of Pelton wheel, draft tubes are not required because it inherently has got it is used in only those cases where the high heads are available for the fluid to come from. So in case of Francis and Kaplan turbine, head available is very less, but in order to produce the same power, we should require the additional fitting of the draft tube. So this is a continuation to the previous problem. The function of the draft tube is to convert the velocity head into pressure head at the runner exit, convert the pressure head into the velocity head at the runner exit, streamline the flow in the tail race, eliminate the eddies at downstream. So I have already discussed it. It converts the velocity head to pressure head at the runner exit. So option 1. It converts the velocity head to the pressure head at the runner exit in order to make maximum use of the velocity and to convert that into power. We fit this draft tube at the end of the turbine, especially in case of reaction turbines. Find the correct sequence of following turbines in increasing order of their specific speed: Francis turbine, Pelton wheel, propeller turbine. So since these reaction turbines operates at a lower head, since they can operate at a lower head in order to produce the same power, they need to have a higher specific speed. So the lower head, it is a Kaplan turbine or the axial turbines which operate at the lower head. Axial turbines are two types. One is the Kaplan turbine and the other one is the propeller turbine, where the blades can't be modified or the blades can't be the shape as well as the arrangement of the blades can't be changed. In the case of propeller turbine, it's an axial turbine. So this propeller turbine can operate at a lower head. In order to operate at a lower head, they and produce the same power, they should be having the highest specific power, specific speed. But correspondingly, at the other end of the spectrum, it is the Pelton wheel. Since it has got the advantage of a higher head, it does not require that much of a higher speed to produce a same power. So the order varies in the form of the lower specific speed to the Pelton wheel, and then the Francis, and then the propeller turbine. So the answer is 2, 1, 3. Look into the next problem. It is a numerical question that in order to calculate the unit quantities. A turbine with an overall efficiency of 85% is to be installed in a hydroelectric plant. The head and discharge available at the plant are 25 meters and 45 meter cube respectively. If the specific speed of the turbine is 230, determine the unit speed, unit discharge, and unit power. So, in order to calculate the value of the unit quantities, we need to know the formulas of the unit quantities. We know the head available, discharge available, and the specific speed also is an available quantity. It's a known quantity. And in this particular problem, we need to calculate the value of the RPM for the speed and the value of the power. And if we know both these quantities, we can determine the value of the unit quantities. Before that, we need to know the formula of the unit quantities. How to derive the formula of these unit quantities. For example, in the case of a unit speed, in order to determine the unit speed, we can write that U or V is directly proportional to root of H. So this U and V can be correspond to the RPM. So N is directly proportional to root of H. So we can write N equal to a proportionality constant K, and we can take it to be equal to root of H. N is equal to K1 into root of H. Unit quantities is obtained when the value of the head is equal to 1. The unit speed corresponds to that particular speed where the head is actually unity or 1. So Nu is equal to K1. Substituting it back, we can write N is equal to Nu into root of H. Therefore, Nu at any particular operating condition is given by N divided by root of H. That is the unit speed calculation. The formula is Nu is equal to N divided by root of H. Similarly, for the unit discharge, Qu, we can write Q is equal to area and velocity. Velocity can be represented in terms of root of H. So Q itself can be written in terms of root of H. So applying the proportionality constant Q is equal to K2H. The unit discharge is equal to K2, then corresponding to H is equal to 1. Substituting it back, we can write Q is equal to Q2 into root of H. Qu into root of H. Therefore, Qu can be written as Q divided by root of H. Similar to that of the specific speed. Now to calculate the unit power. This analysis is very similar to that of the unit speed and unit discharge. Unit power, Pu. The formula for power is overall efficiency multiplied by the power which is available at the inlet. That is rho G into Q into H. So in effectively, P is directly proportional to Q into H. That is, P is directly, that would effectively come to Q itself is directly proportional to root of H. So P is directly proportional to H raised to 3 by 2. Applying the constant H raised to 3 by 2, that is P is equal to K3 into H power 3 by 2. K3 is the proportionality constant. And for a unit head, the corresponding power is called the unit power. So PU is equal to K3. Therefore, substituting it back, we can get P is equal to PU into H raised to 3 by 2. Therefore, PU is equal to P divided by H raised to 3 by 2. The unit power, the formula is equal to P divided by H raised to 3 by 2. So using this analogy, we have determined the value of the specific speed, the unit speed, the unit discharge, and the unit power. In this particular problem, we have the specific speed as well as the overall efficiency terms. We should determine the power, operating power, and we should determine the operating speed. And using this operating speed, operating power, and the discharge which is given in this particular problem, we can calculate the actual values of unit speed, unit discharge, and unit power by substituting it in. So in this particular problem, the overall efficiency is given as 0.85. The head is given as 25 meters. Discharge is given as 45 meter cube per second. And the specific speed is given as 230. So corresponding to 230, it can be referenced. Similar to that, this 230, this quantity 230 is the specific speed in terms of RPM. So corresponding in terms of the corresponding quantity in terms of this particular quantity of 230 is in terms of radian per second, and the corresponding quantity for the RPM can be written as omega divided by this ns divided by 230. So the corresponding in order to make it a bit more clear, Lucy, we can write it as omega s, that is a specific speed in terms of r radian per second quantity, and corresponding specific speed in terms of RPM can be written as omega divided by 2 pi, omega s divided by 2 pi, and that is 230 divided by 2 pi. Multiplied by 60. So that will be coming around 230 divided by 2 pi into 65. So it will come to around 2200 RPM. So that is a specific speed in terms of dimensional quantity of RPM. Now we can move to the real problem. So we need to determine the value of the power. Eta overall efficiency is equal to 0.85 is equal to the power divided by rho g into QH. We can determine power as overall into rho g QH. So that is 0.85 into 10 cube into 9.81 into the Q, that is a discharge. In this particular problem, it is given as 45 meter cube per second. And the head is 25 meters. So it will come around to 9380.8 kilowatt. So that is the power. We can denote it by equation 1. Now the next part, we need to determine the RPM or the operational RPM. So that requires a specific speed calculation. So n specific speed is equal to n root p divided by h raised to 5 by 4. So in this particular problem, this is a dimensional form of n. Beg your pardon, there was a small correction. In this particular problem, the specific speed is a dimensional quantity. So there was a small correction. I made a mess of it. I'm sorry. So this specific speed of the turbine is 230 RPM. This quantity is 230 RPM. So this is a dimensional quantity. So we need not do all these values. So we could have directly written it as the specific speed as 230 RPM. So we can write this is 230 into n into root of T power, that is 9380.8 kilowatt divided by the head 25 into 5 raised to 5 by 4. That corresponds to the value of n is equal to 132.75 RPM. So in this particular problem, we can calculate the unit speed, unit quantities, unit speed, unit discharge, and the unit power. We determined the unit speed nu is equal to n divided by root of h. the QU is equal to Q divided by root of H, and PU power is equal to P divided by H raised to 3 by 2. So N is equal to 132.75 divided by root of H value is 25. So it is coming around 26.55. Q divided by root H, that is 45 divided by root of 25, it is 9. And power P unit power is 9380.8 divided by 25 raised to 3 by 2. So that is coming around 75.046. So this NU unit speed will be having the units of N divided by root of H. N unit is RPM and H unit is root of H unit is root of meter. So it will be a unit quantity with unit, the unit speed quantity. Unlike the dimensional form of the specific speed. So in the one of the previous discussions, I told that the unit of the specific speed could be represented in the form of dimensionless and the dimensional form. So in this particular problem, this 230 corresponds to the dimensional form of the specific speed in terms of RPM. If it is represented in terms of the dimensionless quantity, it should be written as N root P divided by rho divided by G H raised to 5 by 4 in the case of a turbine. Here in this problem, since it is directly given as 230 RPM, we could directly put that in the equation, substitute the values, and then we can get the value of the operational RPM using the operational RPM and the head. Similarly, the operational discharge and head, and similarly, operational power and head, we can calculate the unit quantities in each and every cases. So the next question is regarding a Kaplan turbine. A Kaplan turbine develops 20 megawatt when running at 130 RPM under a height of 20 meters. The outer diameter of the runner is 4 meters and the half diameter is 1.8 meters. The hydraulic and overall efficiency of the turbine are 90% and 85% respectively. Determine the discharge through the turbine and the blade angles at the inlet and outlet measured at mean radius of the runner. In this particular problem, power is given as 20 megawatt, 20 into 10 power 6 watt. RPM is 130. Head is 20 meters. Outer diameter is 4 meters. Half diameter is 1.8 meters. Hydraulic efficiency is equal to 0.9. Overall efficiency is equal to 0.85. We can determine the flow discharge component or the flow rate from the overall efficiency. So Q is written as power divided by rho G H into overall efficiency. So power 20 into 10 power 6 divided by 10 cube into 9.81 into H head is 20 meters multiplied by the overall efficiency. Overall efficiency is 0.85. So you get the value of discharge of the flow rate as 119.92 meter cube per second. So we need to calculate the flow velocity component from the discharge. Flow velocity CF1 is equal to discharge divided by the area in the case of Kaplan turbine, the area which is available is the cross-sectional area, the annular area between the two diameters, the outer diameter and the hub diameter. So it will be pi by 4 into the outer squared minus the hub diameter. So 2 divided by pi by 4 into outer diameter is 1.8 squared. Outer diameter is 4 squared and the inner diameter or sub diameter is 1.8 squared, and corresponding flow velocity term at the inlet is equal to 11.96 meter per second. The mean diameter dm is equal to d outer plus d half divided by 2. That is 2.9 meters. In this particular problem, we need to calculate the blade angles at the inlet and outlet and the discharge through the turbine. So we have calculated the discharge through the turbine. Now we need to calculate the blade angles part at the inlet and the outlet. And that should be measured at the mean radius. And that's why we have calculated this mean radius of the runner. Now we need to calculate the tangential velocity of the runner at the mean diameter. In this tangential velocity, we can determine the tangential velocity or the blade velocity of the runner. We can calculate the tangential component of the velocity, and using this tangential component of the axial velocity, flow velocity term, and the peripheral velocity or the blade velocity, we can calculate the blade angle at the inlet, and similarly at the outlet, we can calculate the blade angles. And for that, we need to draw the velocity triangle. So in the case of a Kaplan turbine, so we can draw this to be the C1, that is the axial velocity term. This is the blade velocity V1. This one is the velocity VR1, or we can write it to be VR1 for easiness of understanding. We try to extend it to here. The relative velocity term, the angle which the relative velocity term makes with that of the blade angle, that is the blade angle term. This can be as alpha 1. This no, the 1, and this can be written as the alpha 1 term. This one, this particular quantity, this particular velocity quantity is CF1. and this particular quantity is one. This particular quantity, is C theta 1. So in this particular problem, we need to calculate the tangential velocity, and similarly at the outlet also. Outlet, it's an we can assume it's a Kaplan turbine, so to be a no swirl flow. This at the outlet, if this is the CF2, that is equal to CF1, that is equal to C2. This one will be the U1, and this one will be the relative velocity VR2 at the exit. So the angle, this one will be the blade angle, and this one will be 90 degrees. So we should calculate the tangential velocity at the inlet based on mean diameter. U1 is equal to mean into n divided by 60. So this U1 and U2 will remain the same in cases. Since we are calculating this at the mean diameter. So U2 is equal to U1 is equal to pi dmn divided by 60 pi into d mean. That is 2.9 into 130 divided by 60. You'll get it around 90.73 meter per second. Now the second step, we need to calculate the tangential component of the flow velocity, tangential component of the axial velocity term. So we can determine it from the hydraulic efficiency. So hydraulic efficiency, eta hydraulic is equal to C theta 1 into U1 divided by G into H. From this, we can calculate C theta 1 is equal to GH into hydraulic divided by U1. GH is 20. Hydraulic efficiency 0.9 divided by U1, that is given by 19.72. So we'll get the value of C theta 1 to be equal to 8.95 meter per second. So we have both three parameters, U1, C theta 1, and VF1. In this particular problem, since the outlet velocity triangle is a right angle triangle, it's a no swirl flow, we will be getting the flow velocity term same as that of the actual velocity, and nothing is mentioned regarding the friction for the flow. We can take the flow velocity component remains the same to maintain the same conservation of mass through the turbine. So now we can calculate the blade angles from the inlet and outlet velocity triangles. From the inlet velocity, this is the inlet velocity triangle, and this is the outlet velocity triangle. From the inlet velocity triangle, if you take the tan of tan of beta, so that is a combination of a tan of beta. This is the you could write it to be beta dash. Beta dash is equal to 180 minus beta. So if you write it like so, it will be tan of 180 minus beta equal to CF1 divided by 1. So that will become effectively smaller angle will become if you represent beta dash, so that beta dash will become equal to CF1 divided by C theta 1 minus U1. CF1 we have determined from the discharge and overall efficiency term to be 11.96 meter per second. C theta 1 is equal to 8.95, and the corresponding U1 value is 19.73. So this value show that the triangle which we have considered is slightly wrong. So this is one method by which we can cross verify whether the triangle which we have drawn is right or not. So using this, we can write 11.96. We just replace the signs to be 9.73 minus 8.95. So that will be coming around 47.95 degree. So the corresponding angle will be 47.95 degree at the inlet blade. And similarly at the outlet velocity triangle, and beta 2 equal to CF2 divided by U2. So CF2 we have determined it to be same as CF1 itself. So 11.96 divided by 9.73. That implies B2 is equal to 31.21 degree. So since we have found out that the velocity triangle that we have drawn at the exit is not the correct one, we can redraw it using the answers which we have got. So a few parameters will be slightly shifted in the other directions. Here, we'll get the blade angle to be equal to 47.95. So we have to draw it in such a way that it makes sense. So the whole velocity is U1. This will be the beta 1 term. This will be VR1 relative velocity term, and will be CF1, and this particular quantity, the quantity which is here to here, that is the C theta 1 quantity. So this now will be equal to U1 divided U1. So this in this particular problem, this particular quantity is C theta 1, and this but So in this particular problem, this particular quantity is c theta 1, only this much. The difference between u1 and c theta 1 will be this horizontal component, this much, and this one will be the vertical component cf1. And using these two parameters, we can calculate the value of the blade angle at the inlet, and that blade angle will be making will be in a different direction. And correspondingly at the outlet, the velocity triangle will appear like this. So this is one way in which we can just modify our velocity triangle based on the results that we get from the problem. So in this particular problem, we have determined the flow velocity component, tangential peripheral blade velocity component at the mid diameter, and the tangential component of the velocity. And using this, we have calculated the blade angles at the inlet and the outlet. So that completes the session, the problems that we were planning to discuss for this week. In this week, we have discussed a few multiple choice questions and numerical answer questions based on the Kaplan turbine, the draft tube, specific speed, and general problems based on the previous week's lectures. If you have any doubts, you can post it in the forum, which is available in the NPTEL course website. In the next week's lecture will be the last lecture for the last tutorial session for this course, and that in that we'll be recapitulating what we have learned in the previous 12 weeks. A few revision. It's more like a revision with a few multiple choice questions and numerical questions based on these lectures, and that will give you a brief overview of what we have learned in the lecture, and that will be a good experience for you before the exam to just revise yourself as well as uh, to basically to recapitulate. That's it. Then hope you have enjoyed. Thanks for the patient listening. Thank you.